Gnanam paramam dheyam. Knowledge is supreme.
We have been talking about these rules that allow us determine the symmetries of electronic states, right. When we say electronic state, we have understood that we mean what is the symmetry of the, and when I say symmetry, I definitely mean which symmetry species or which irreducible representation. So, symmetry of states means irreducible representation to which the electronic wave function belongs, alright. The way I get the electronic wave function is by a continued product of all the occupied molecular orbitals. So, we have seen all the easy cases yesterday, we will see another easy case today. So, what have we said earlier? We have said that the way you determine the symmetry of a state is that you take the product, right, direct product of everything, and you basically multiply the representation, see what you get. So, if all the MOs are doubly occupied, then what happens? Each of them give rise to a totally symmetric representation, right, because something multiplied by something else, so something multiplied by itself is totally symmetric. That is something that we have learned while we discussed the normal modes of vibration. Same thing holds here. Then we said that suppose you have one electron in an orbital which is not paired. Okay. Example would be say He2 plus, one electron in an orbital. So, there is only one singly occupied molecular orbital. In that case, whatever is the symmetry of that orbital is the symmetry of the state, because everything else is totally symmetric anyway. Then we said what happens when we have two electrons in two non-degenerate orbitals. You take a direct product, and then when you take a direct product, it is not necessary that you are going to have a single state, because a direct product more often than not leads to a reducible representation. If both the wave functions participating in the direct product are one dimensional, if both the wave functions belong to one dimensional representations, then their direct product is also one dimensional. But if any one of them is more than one dimensional, then you get a reducible representation, not an irreducible representation. Alright, are we clear about that? I have two irreducible representations, say gamma I and gamma j. If I take a direct product of these to get something gamma, then if this is one dimensional and if this is also one dimensional, then the product is one dimensional. If one of them is one dimensional and the other is two dimensional, what is the representation that you get by doing the direct product? What is the dimensionality of the representation that you obtain from the direct product? Yes, 2. And if this is 3 dimensional and this is 4 dimensional, then what is the dimensionality of the product? Yeah, 12. And more often than not, usually these are all reducible representations, that is what I am saying. So, you should be able to reduce them and get a sum of irreducible representations. We are going to encounter a situation like that right now. What we did not discuss last day and we will discuss today is what happens when you have two electrons in two degenerate orbitals. Of course, everybody is familiar with an example of such a situation. What is that example? I need to hear you. Oxygen, it is written on the board, right? Oxygen. Everybody knows the electron configuration of oxygen. Dioxygen is something like this. I am not drawing the arrows intentionally. It is like this, right? What are these orbitals? What are the homos for oxygen, dioxygen? Pi star. So, pi star means what? Pi g or pi u? Pi g. So, we have great respect for orbitals that are symmetric with respect to inversion. So, those pi orbitals are called pi g, right. If they are ungerade, then we do not call them G anymore. Okay. So, how will I determine the symmetry of this state? The basic working is the same, right. You still take a product of the two, alright. So, first let us take the product and see what happens. This is pi g, this is also pi g. So, what we need to do is we need to take the direct product pi g cross pi g. What is the symmetry point group of dioxygen? D infinity H. So, say that. What is the problem in saying that? D infinity H. So, we need to see D infinity H character table. This is D infinity H character table. As usual, we will do the long cut first and then we will learn the shortcut. Okay. Pi g cross pi g. What is pi g? This is pi g and once again this is pi g, right. So, what is pi g cross pi g? What are the characters that you get? So, 2 into 2 4. What is the second one? What is the character of C infinity? 5. Yes. 4. 4 cos square 5. Four cos square 5. What is the third one? Third one is very easy, even I can do it. 0 multiplied by 0 is a 0. What is the fourth one? Vibha. Pi g cross pi g. इधर बाबा fourth one cos square तो हो गया. ये क्या है? What happens when you multiply 2 by 2? 4. Excellent. Then yes, 4 cos square 5 again, plus or minus. Okay, if you say so. Then 0. Okay, that is where the character table ends. I got confused because I was wondering where this RXRY came from. That is actually the next column. Alright. This is the representation that I have got. Okay, and at least looking at this character table, this is definitely a reducible representation. How do I reduce a reducible representation? What is the formula?
1 by h.
1 by h. Problem is h is infinity here, right? Right? H is infinity. So, you will not be able to use the formula. How do I do it? I do it the hard way. Now, you have to slug it out. You can still do it, but you cannot use the formula. You have to do it by inspection. Let us see if we can do it by inspection. And usually when I do things like this, I always go wrong and students get it right. So, I am hoping that you are going to get it right now. So, let us see. What is it? First one is 4, right? How do I get 4? No, even before the first one, let us look at the character of I. Because the good thing is, since there is a point of inversion, you either have G or U, right? Looking at I, we should be able to tell what kind of thing we get. In fact, we do not even have to do that. We are doing pi G cross pi G, right? What did we discuss in one of the earlier classes? What is G cross G? G cross G is G. U cross U is G. G cross U or U cross G, that is U. Okay? So, we do not have to bother about these. We should only worry about these. So, when we try to do it in the brute force way, we should only look at the J-Rade ones. Okay? And I have got 4. So, how can I get 4? Many combinations. I can add this and this, or I can add this and this and this, or I can have pi g plus 2 into sigma g plus, or I can have pi g plus 2 into sigma g minus. There are many ways, or I can have 4 sigma g plus or 4 sigma g minus. So, let us see what it will be. To do that, what is the best term? Let us see what is this one. 4 cos square phi, right, and there I have 2 cos phi. It might be a little easier if I try to tackle that first. Now, how do I write cos square phi? I think we all know that. Cos square phi, because my hope is here I have cos phi, here I have cos 2 phi. So, if I can somehow, and I have a square, everybody knows cos square phi is related to cos of 2 phi. So, from there I get a hint that maybe delta G is involved. So, let us see if I can write that cos square phi 2 cos square phi minus 1 is equal to cos of 2 phi, isn't it? So, I have, what do I have here? I do not have cos of 2 phi, I have cos 2 phi multiplied by 2. How do I get that? Multiplied by 2, this becomes 4 and this becomes 2. 4 cos square phi minus 2. Yeah. So, 4 cos square phi is something I already have. How do I get minus 2? Am I making sense? No? So, what I am trying to do is I am trying to write this as gamma, this is your gamma, right, this is what you have got. I am trying to write it as something like A1 multiplied by sigma G plus, I will write like this, maybe write like this, sigma G plus A2 multiplied by sigma G minus plus A3 multiplied by pi G plus A4 multiplied by delta G. I need to find A1, A2, A3, A4. I don't need to worry about the U's. So, how do you find A1, A2, A3, A4? That is all I am saying. Can you do it? So, you saw what I am doing, right? I am trying to look at individual characters and from there I am trying to figure out what the coefficients are. Tell me what the coefficients are. Delta G is definitely there is no doubt. So, one thing is if delta G is there, delta G is a 2-dimensional basis, right. How many dimensions are you left with? The reducible representation you have is 4 dimensional. So, it is either delta G plus delta G or it is delta G plus sigma G plus sigma G minus or it is delta G plus 2 sigma G plus or it is delta G plus 2 sigma G minus. Actually, one thing we can do without getting into much trouble is that just tie them out. Can it be 2 delta G? 2 delta G does not match, right. Can it be delta G plus 2 sigma G plus? No. Can it be delta G plus 2 sigma G minus? Then I am only left with delta G plus sigma G plus sigma G minus. Does that give you the same answer? Yes? Actually, that is a better way. I think I was going in a very roundabout manner, it is not required. So, what we get is, we get that pi G cross pi G, this gives me delta G plus, or maybe I will write the 1-dimensional reps first. I will erase this because this is not required. It is sigma G plus sigma G minus plus delta G. You agreed with that? Sorry? Work it out, see if it will work. Delta G you have the characters 2, 2 cos phi etc., etc. If you add 2 sigma G plus, what will you get? 2 plus 2 4, that is okay. But then you get 2 cos 2 phi plus 2, that is also okay. 0? 0 is not coming. Somewhere it will go wrong. You will always get a unique combination, there is no doubt about that. That is one good thing about symmetry. If you go wrong, it is very easy to figure out that you have gone wrong. Alright. So, this is what it is. So, this is the brute force method. It is not all that difficult also. But then if we really want to be lazy, then what we need to do is, we need to know another kind of table over and above character table, that is called the product table. So, see, actually these product tables are also available. And you might notice that the sigma G and all are not mentioned here. What is given is just sigma plus sigma minus pi. So, this is what is given. You take pi sigma minus, what do you get? You take sigma minus, what do you get? So on and so forth. Just looking at the table you can figure out, and then G or U, that comes from what is that? G cross G or G cross U or U cross G or E cross U. Okay. So actually product tables are there, but at least for this course I am not going to provide you the product table. In case I ask you to work out, well, for anything, you should be able to do it. For D infinity H, you have to do it by inspection, or C infinity B. For all other non-infinite point groups, you will be able to use that celebrated formula of ours. Okay. So, let us not bother about product table. Let us see what we have here. What have we determined so far? We are working with oxygen. Oxygen has 2 electrons in the degenerate pi j orbitals. We have worked out what are the symmetries of the states that are generated by taking a direct product of the symmetries of these two, pi j and pi j. Okay? 3 kinds of states are generated. Okay? How many states is this? This is 1, this is 2, and this how many? Delta G gives you how many states? 1, 2, 3, 4, infinity. 2 is a 2-dimensional representation. Now, let us see. What had we done earlier? What had we done for say helium star? Did we discuss helium star the previous day? Helium star means 1 electron in sigma u, 1 electron in the upper 2 sigma g. Understand what I am talking about? For homonuclear diatomics, what is the lowest molecular orbital? It is sigma g plus, right? I call it 1 sigma g plus. This is 1 sigma u plus or minus. Plus or minus. If you have forgotten, let us do it quickly. This is the MO. What is the character of E? That is 1. What is the character of C infinity? Minus 1. Okay, that is what makes it U. What is the so basically it's either this or that, right? So sigma V, if I give sigma V, is it plus or minus? Plus. Then what is it? Is it sigma U plus or sigma U minus? I think I went too fast and confused people, right? Are we clear? Are we all on the same page on this? What I am saying is, this is your antibonding orbital. Okay. Let us see what are the characters for each symmetry operation. For E, it is plus 1. For C2 is C infinity, what is it? Oh, it is not minus 1. That was the confusion. Is it? Yes, it is plus 1. And for what is the next one? Sigma V. Sigma V is plus 1. Then I minus 1. That's why it is U. I somehow in my mind I confused small I with C infinity. Okay. What is the character of sigma V? You said plus, right? And I is minus. So sigma V plus I minus is this combination. So it is sigma U plus. You can go ahead and work out the rest, you will see it. It is 1 sigma U plus. Next one is, you can think the sigma orbital formed by combining two 2s, bonding combination of two 2s orbitals, that is again I will call it 2 sigma G plus. So what I am saying is, for helium 2, this is the ground state configuration, right? So if I move 1 electron, I promote 1 electron from here to here. What is the symmetry of that state? 1 electron is in sigma U plus, the other one is in sigma G plus. So symmetry of this state is sigma G plus cross sigma U plus. What will that be? What is sigma G plus cross sigma U plus? As long as we know the table of 1, we should be able to figure it out. If we do not know the table of 1, then we got a problem. Do we all know the table of 1? Who among us does not know the table of 1? Looks like many do not know the table of 1. Should I recite it? 1 1s are 1, 1 2s are 2, 1 3s are 3. So sigma G plus is all 1s, right? So the direct product is sigma U plus. This we had done. Okay. Then what did we do? We said that the sigma U plus we can get singlet as well as triplet. Remember that? Sigma U plus can give you 2 states actually. One is singlet sigma U plus and the other is triplet sigma U plus. I am not talking about oxygen right now. I am talking about the excited state of helium 2, not atom helium 2. So that is one singlet sigma u plus and triplet sigma u plus. Okay. What would be the wave functions for that? What is singlet sigma u plus? For that, the spatial part is symmetric, right? Spatial part is symmetric. For this, it will be sigma u plus, let us call the electrons 1 and 2, 1 sigma g plus is electron number 2. Is that a good enough spatial part? What do I have to do? I have to take the other combination sigma u plus 2 sigma g plus 1 and then I can take plus or minus, right. If I take plus, then the spin part has to be alpha beta minus beta alpha. If I take minus, then the spin part has to be alpha alpha or beta beta or alpha beta plus beta alpha, remember. So, both are possible. The first one is singlet, second one is triplet. So, if we proceed along the same lines here, then we can assign singlet and triplet to every one. Okay. How many states do we get? From here, if we now incorporate the spin part, I should get singlet sigma g plus, triplet sigma g plus, singlet sigma g minus, triplet sigma g minus, singlet delta g, triplet delta g. How many states is that? 8. I have got the first answer 8. How many agree with 8? How many disagree? If you disagree, what is your answer? 10. So, I have got a bid at 8, I have got another bid at 10. Do you have any other bid? We will sell to the highest bidder. 12. Now, this is getting arbitrary. You have to justify why 12. Achha, each singlet state is how many states? 1. Each triplet state is how many states? Then why do I call it triplet? I would have called it doublet. Triplet state is 3 states, isn't it? Remember, that is why we are repeating that so many times. Alpha alpha, beta beta, alpha beta plus beta alpha, 3 states. Alright. We are just obsessed by the book written by the ex-IIT and that is why we stop at 2 states. Not necessary, we can have 3 states. Triplet, right? Triplet is 3 states. Okay. So, let us now count. Singlet sigma g plus, how many states is that? 1. So, let us count 1. Triplet sigma g plus, how many states? 3. So, 1 plus 3, 4. Singlet sigma g minus, how many states? 4 plus 1, 5. Triplet sigma g minus 8. What about these? Singlet delta g, how many states? 9. 2. So, 8 plus 2, 10 and triplet delta g, how many? 6. So, 16 states, alright. 16 states is what we get from this electron configuration of oxygen. This ground state electron configuration of oxygen seemingly gives rise to 16 states, but there is a problem actually. Not all these 16 states are acceptable. We just assign singlet and triplet to everything, anything and everything, right. That is not necessarily the case, because here the thing is, here you have 2 electrons in degenerate orbitals, right. So, their spins are actually correlated to each other. Let us see if I can draw boxes and try to see how many states I actually should get. Second, remove. Those who have studied term symbols and all will be familiar with this treatment. I will draw it like this. I am drawing 4 boxes. So, this is my orbital A, this is orbital B, this is A, this is B, alright. What are the 2 spins possible, up and down? I will draw 2 arrows for those, or I will write alpha beta, something like that. In how many ways can I fill in 2 electrons here? I have 2 electrons, right. How many ways should it be? 4 places and 2 objects, 2 identical objects. How many ways can I fill 4 places with two objects, two identical objects, yes. 4C2, how much is 4C2? 6. Why is it not 4P2? Yeah? Yes, the objects are identical, right? Permutation comes only when you distinguish between the objects. Here the combination is the only thing that is important. So, we know that we should be able to draw 6. So, let me draw 6 boxes first. So, I will fill in the electrons, I will just draw circles or something. This is one way in which I can fill. Number 2, number 3, number 4, 5, 6, right. So, what I am saying is there should be only 6 states, not 16. So, there must be some way by which I should be able to eliminate 10 out of the 16 states that I have generated here. How do I eliminate? Any guess? Pauli principle, what is Pauli principle? The overall wave function, total wave function means space part multiplied by spin part has to be antisymmetric with respect to exchange, right? Right? Total wave function has to be antisymmetric. So, let us see how many of these are antisymmetric, how many of these are symmetric. To do that, first of all, let us think singlet and triplet, which ones are symmetric, which ones are antisymmetric. The spin part, is singlet symmetric or antisymmetric? And triplet is symmetric, right. So, I should write singlet only with the symmetric space parts, I should write triplet only with antisymmetric space part. Now, which of these space parts are symmetric, which are antisymmetric? Sigma G plus, is it symmetric or antisymmetric? Sigma G plus is totally symmetric representation, right? Right or wrong? So, it is symmetric, of course. So, should I write singlet sigma G plus, or should I write triplet sigma G plus, or should I write both? Do you understand what we are trying to do here? If the space part is symmetric, then the spin part must be antisymmetric. If the space part is antisymmetric, then the spin part must be symmetric. Alright, we agree so far? Now, what I am saying is this, sigma G plus, I hope we all agree, is totally symmetric. So, the spin part must be antisymmetric. So, between singlet and triplet, which one is antisymmetric? Singlet, alpha beta minus beta alpha, right? Triplet is alpha alpha, beta beta, alpha beta plus beta alpha. Triplet is symmetric. So, only singlet sigma G plus will survive, triplet sigma G plus will not be there. So, I will just write singlet sigma G plus will be there. Okay. If I go to sigma G minus and delta G, now what happens? Yeah? Triplet, which one will be triplet? Actually, it is easier to work with your one dimensional representation. So, let us just see what sigma G minus is. So, sigma G minus, if you look at the characters, so if you apply, well, you cannot use I, you have to think of operations that cause an exchange, right, and if any of these operations have a character of minus 1, then it is antisymmetric. So, I, okay, is plus 1, no problem. What about C2? C2 causes an interchange, right, C2 causes interchange, right. So, what is it then? Is sigma G minus, should it be symmetric or should it be antisymmetric? Antisymmetric. So, if the space part is antisymmetric, what should the spin part be? Symmetric. Triplet. So, I get singlet sigma G plus triplet sigma G minus, and in fact, to get the third one you can even cheat, you do not need to even understand, just see how many we have got. We are going to get 6 states, you know that, right? How many have we got so far? 1 plus 3, 4. How many more? 2 more. If I write 1 delta G, that is enough. So, it has to be singlet delta G. right, because triplet delta G is how much? It can never be triplet delta G, right, because triplet delta G would mean 6 states there already. Total you are allowed to have 6 states. So, it will naturally not be triplet delta G, okay. And to understand why delta G is, so what is it, symmetric or anti-symmetric? It's symmetric, right. That may be a little difficult because it's 2 dimensional, we will not go there, but it is not very difficult. If you work out the singlet, if you work out the 1 dimensional representations first. So, this is what we get, singlet sigma G plus triplet sigma G minus plus singlet delta G, alright. How many states? 1 plus 3 plus 2, 6. So, what are we saying here? We are saying that out of this electron configuration, we actually generate 3 states. See, in our earlier discussion of oxygen, all of us know that the ground state of oxygen is triplet. And the way we have got it is that we said there are 2 degenerate orbitals, so the electrons should be parallel to each other. Here we are doing a little more detailed treatment of it. We are saying that you can actually get 3 states. However, since the electron configuration is same, you look at these, you have 2 singlet states, 1 triplet state. Which one will have lower energy? Hund's rule? Hund's rule? And this time even electron configuration is same. So, triplet state will have lower energy. So, of the same, this is the part that we need to understand very well, that even for the same electron configuration, we can actually get different states of different energy, alright. So, what you get is, you get 3 states, the lowest of which is your triplet sigma G minus, alright. What will be the second lowest state or second highest state? In this case they are the same, and what will be the highest energy state? See, first what have we used so far? To identify the lowest energy state, we have used Hund's rule. Now, if you look at the other 2, both are singlet, sigma and delta, both are singlet. Now, Hund's rule will not work. What will I use then? This is singlet, this is also singlet. Do they have same energy or do you expect them to have different energies? Different energies. That we can even tell intuitively. Which one should have lower energy and why? Okay, half the people say sigma G plus, half the people say delta G plus, delta G, half will be right always, right. So, if you say sigma G plus, you have to justify why. If you say delta G, you have to justify why. Which one has more degeneracy? So, which one should have lower energy? Delta G. So, if spin states are same, usually degenerate ones have lower energy, right. So, this is what you have, singlet delta G and this is singlet sigma G plus. So, ground state of oxygen is still triplet. The 2 excited states immediately higher in energy are still singlet. And I will just write the energy values, you do not need to remember them, 7882 and 13121. This energy gap is 7882 centimeter inverse and this is 13, yeah, such bad memory here, 121 cm inverse. We will come to the implication of these. Swati, do not get distracted please. So, 7882, what kind of radiation would that be? Microwave, IR, visible, UV, X-ray, gamma ray. What would it be? 7882 centimeter inverse. 13121 is I think something like 572 nanometer or 672 nanometer, forgotten. Visible red. So, this is red 13121 centimeter inverse. This one is near infrared 7882, right. So, you kind of get the idea of what kind of energy gaps are there. Now, tell me something, do you expect transition to take place between triplet sigma G minus and any of these levels? That has been forbidden, right? Right? So, actually you do not expect too much of transition to take place. But when we say forbidden, forbidden is never 100% forbidden, a little bit of cheating is always there. So, that is why what happens is, has anybody seen liquid oxygen? No, no. Liquid oxygen is blue in color. Liquid oxygen is actually blue. Why? Because of this. Not because it is paramagnetic, because this its 13.121 centimeter inverse is absorbed. So, you see complementary color. Last year, about a year ago, there was an accident in Professor Maheshwaran Shanmugam's lab, and apparently the accident happened because some oxygenation reaction was going on at low temperature. So, liquid nitrogen was there and then oxygen was being passed. So, oxygen condensed, and the student performing it wanted to see what is this blue little liquid that has formed. So, he took off the glasses, went very close, and that is when the apparatus decided to burst. So, fortunately, no serious damage to him happened, but then there was so much blood, it was scary. So, please be careful when you do such experiments. You should never liquefy oxygen. Liquid oxygen is explosive, right? But the point is, it is blue. That is one thing we learned from here. But then you do not see the blue color in gaseous oxygen, right? Why do not you see blue color in gaseous oxygen? Because it is too dilute and the spin forbidden transition is not seen. But when you condense it, you can see even that. That is point number 1. Point number 2 is, those of you who, well, everybody, we have all seen ads of these creams and stuff, right? Nivea cream and so on and so forth. Very often do not they say that it is enriched in antioxidants, right? Or people tell you that you should eat a lot of fruits, that is how you get antioxidants. So, where is this fad from antioxidants, where does that come from? What is the issue with oxidant? The issue is this: ground state is triplet, excited states are singlet. So, if you can somehow take oxygen to singlet states, it becomes very, very reactive, and that is what happens, that is what causes things like aging. Singlet oxygen in your skin causes wrinkles to appear, right. So, these anti-aging skins, they claim that they have something in that cream that will react with that singlet oxygen quickly, so that you still look young. Okay, none of you need that right now, that is like 15-20 years later, but that is what it is. And it is actually something that shows up in a disease and in a therapy. How many of you know of the disease called porphyria? The porphyria, does it remind you of some chemical, some molecule? Porphyrin, right? So, cattle often develop this disease called porphyria, because the thing is simple. Cattle eat grass, grass contains chlorophyll, chlorophyll contains porphyrin. So, degradation product of chlorophyll is not supposed to come to the skin. In this disease, what happens is, it comes and accumulates in the skin of cattle, and then when they graze in the sun, this porphyrin kind of molecules, before we start entertaining again, porphyrin kind of molecules are very good, what are called photosensitizers. Those of you who are studying the photochemistry course will perhaps have encountered the term or will encounter the term photosensitizers. As we said, it is not so easy to go directly from here to here, right, but you can have an organic molecule, right, which you excite from singlet to singlet state, then it goes from singlet to triplet state, and then that triplet state reacts with this triplet ground state of oxygen to produce singlet oxygen. That kind of a molecule is called a photosensitizer. Porphyrin is a good photosensitizer. So, in this disease, what happens is, when cattle go out and graze in the sun, this accumulated porphyrin in the skin causes this photosensitization, production of singlet oxygen, and that is what gives them blisters. It is actually a very painful disease, and in very, very rare cases, even human beings can have porphyria. I knew at least one such person. So, she could not go out in the sun. If she went out in the sun, she would develop blisters. So, that is something that comes directly out of all this group theoretical discussion, a disease, porphyria. and it is also the basis of a treatment. The treatment is called photodynamic therapy, it is anti-cancer, because everybody knows that what are the ways in which one treats cancer? Yes, radiotherapy, anything else? Chemotherapy, right? In chemotherapy, what do? You inject the patient with a lot of poison in the hope that the poison is going to kill the tumor. What happens more often than not is that it kills the tumor, but it kills the patient along with it. That is why it's not, many times you will hear of patients not surviving chemotherapy, right. So, that is why for many decades there has been a search which is not completely successful yet for something that will be very specific to tumors, and again the answer lies in this porphyria. So, somebody had done the experiment once which showed that porphyrins can actually accumulate in tumor tissues and they are photosensitizers, that is known from porphyria. So, can we inject the patient with porphyrin and keep the patient in dark? The porphyrin will go and localize in tumor, and then when you shine light, then this porphyrin is going to form reactive singlet oxygen, and that oxygen will kill the tumor and nothing else, because singlet oxygen is not produced anywhere other than the irradiated portion of the body, right. So, photodynamic therapy is an accepted modality of treatment in USA, and I think I cannot pronounce the name of the hospital, that is the problem, Sri Chitra Tirunal or something like that hospital in Cochin is also doing clinical trials on it. Now, we are in an age where we have a second generation and even third generation drugs for photodynamic therapy, but of course, I only told you the bright side of PDT, it is called PDT, photodynamic therapy. There is a dark side as well, but the point I am trying to make is that all these things that we are doing actually have manifestations and applications in real life as well. Okay, it is not just pipe dream. Okay, so this is what it is. We have learned how to determine the symmetries of states, even of oxygen, which has electrons in two degenerate orbitals. Well, there is not much left to talk about electronic transitions, orbital. We have already said, right, this orbital selection rule. You understand that the triple product has to contain in the transition moment integral has to contain a totally symmetric representation. Okay, that is when it is orbitally allowed. Sometimes what happens is it is not orbitally allowed, it becomes allowed vibronically by coupling of vibration with your electronic motion. So, maybe what we will do is we will start with an example next day, because this totally symmetric representation thing is something that we have beaten black and blue while talking about normal mode. So, we do not have to repeat it. So, let us talk about a specific example. Let us talk about benzene the next day, and in benzene let us see why the spectrum looks like what it does, which of the transitions are totally allowed, which are orbitally forbidden but vibronically allowed.